I thank you all for coming for today's lecture by Dr. Kirane. Thank you, Dr. Kirane, for his interesting lecture, and also special thanks to the Library ID and Chris Sauer, and also Dylan for the tech setup for all these STEM lecture series. So this is the last one of this semester's series, but then for the spring semester, and then we will continue. So please stay tuned for another new series for the spring semester. Before the lecture, I'm going to introduce Dr. Kirane. Professor Kedar Kirane is an assistant professor of mechanical engineering. His research focuses on understanding the fracturing behavior of various conventional and advanced composite materials. These include fiber-reinforced composites, nanocomposites, geological materials, and soft composites. His research combines experimental, computational, and theoretical approaches. Dr. Kirane obtained his PhD in 2013 from Northwestern University and joined the mechanical engineering faculty at Stony Brook University in September 2017. He also holds an MS degree from the Ohio State University in 2007 and a BS from the University of Pune, India, 2004, both in mechanical engineering. Prior to joining Stony Brook, Professor Kirane worked as a senior researcher at the ExxonMobil upstream research company. The presented research herein is supported through a Young Investigator Award from the U.S. Army Research Office. So let's welcome Dr. Kirane.
Thank you very much for the introduction and also the invitation to speak here. It is nice to speak to an audience who is not always specialized in the same field that I am, because they always ask questions which are more critical. So it is nice to talk to a wider audience. So thank you for making time and being here. So I will talk about this topic, but during my presentation, if anyone has any questions, don't hesitate to stop me and ask me questions. So I might, don't say all the questions at the end, because sometimes you forget. If you have a question, no problem. And then answer that. All right. So let's start. Everyone can hear me okay in the back? Can you hear me? All right. So the title of my talk is Predicting Dynamic Fracture of Fiber Composites to Enable Protection of Army Personnel and Infrastructure. So we focus more on actually the first half of the title, which is prediction of the dynamic fracture of composites. Okay. So before I start, I want to acknowledge that the Army Research Office has given me this grant to do this research, so I'm very grateful to them. And also to my graduate students who are actually the ones doing the work. I'm just giving them order. So one of them is right here, Jing. She's in her third year of the PhD. She's doing a very good job. That's here, and also second one is Taufik, who not be here. But yeah, so a lot of it is thanks to you guys. Alright. So let me start. We all must be aware that fiber composites today are like everywhere. They are used in several applications, from very low tech to very high tech. To give you examples, they are predominantly used in the aircraft industry, in transport, in automobiles, in energy industry. For example, they are used to make blades of wind turbines, in storage, in EV applications, and also in exports and labor. Like they are used in a lot of applications around us. We may not be aware, but they are quite everywhere. So why? Why are they used in so many applications? One of the reasons, or not one, there are several reasons why they have excellent mechanical properties. They have very good strength meaning highest load. They have very high stiffness. They are very stiff. I mean, they can be non-stiff also, but depending on the application, you have tune and stiffness. And most importantly, they have low weight. They are lightweight, and therefore they are specific strength, which is like strength per unit weight. That is very high compared to other engineering materials like steel or concrete. Compared to these conventional materials, these have very high specific strength. They also have good resistance to fatigue, which is like failure under loads. They are resistant to corrosion. And another interesting aspect of these materials is that effectively they are microstructured. These materials you can, basically they are layered arrangements, okay? They have like several layers layered on top of each other. And you can adjust the properties of the material by changing the orientation of these layers. So it gives like a tuning parameter to the engineer to adjust the properties of the material depending on the application. So it has a lot of good properties, and that is why they are being used in so many different applications. Now, one of the properties which is of interest in this presentation is their energy dissipation. What I mean by energy dissipation is as follows. Every material, like when you apply a load on that material, it gets stressed, right? So that means it is storing energy in it, and that energy is called strain energy. The only way that energy is released or dissipated is by fracture, by the material breaking, or it can just unload and release the energy back to whatever was loaded. Simple example is you can think of a rubber band, just stretching it. When you stretch it, energy is being stored in the rubber band. So when you just let it go, it goes back to its original shape. So that energy is just released. But that is not dissipation. Okay? Dissipation occurs when the rubber band actually breaks. So that is what I mean by energy dissipation. That is what we are interested in. It turns out that composites also have excellent energy dissipation, which means they can dissipate a lot of energy. And that is why they are used in a lot of applications where impact or crash happens. So I'll give some more examples with the slide after this. This is why it is important to understand and know how to predict this dynamic fracture of fiber composites. By dynamic, I mean fracturing occurring at high speeds under events such as impact or crash. So here I show some examples where composites are used and the structure or the application is subjected to very sudden load like impact. For example, car crashes occur all the time, unfortunately. And today a lot of cars, they have their structures made from composites. And to give an example, this is a component which I showed here. It's black colored thing. That is called a crush can. It is there in almost all the cars. Okay? So imagine if you're driving a car, it has a front bumper, and a lot of times today even that bumper is made from composite. Behind that bumper, there are these cans which are shaped like a soda can. It's cylindrical in shape. And the function of the bumper and then the can is to basically absorb and dissipate the energy of the car. So anytime there is an accident, when it is, let's say, very low velocity, the bumper is what absorbs that energy. For mid velocity, it is this brush can which absorbs energy. And then for high velocity, the entire frame of the car will absorb energy. So this is one great example where we need to understand how this energy is being dissipated so that we can design these components. I mean, if you don't understand it well, it's possible that we don't design it correctly, and then when there is an actual crash, it doesn't dissipate the required amount of energy, which can consequently harm the passenger. So these have to be designed very carefully, correctly dissipate the required amount of impact. Okay. So this is how actually one of the crush cans looks like after it has been impacted. It has fully fractured everywhere, and the fracturing dissipates everything. So the more that it fractures, the better it is. And composites have this ability to go through a lot of fractures and dissipate a lot of this. This is another example of aircraft. And then my project, it deals with military applications. So this is an example of a military bunker, a missile case, and even bulletproof vest. These are all made from composites, and in all these applications, they are supposed to withstand impact loads and dissipate energy by fracture.
After like an accident of some sort where these fibers are completely absorb the energy they break, are they able to be reused or no?
No, it's one time use.
All right.
I mean, yeah, it's one time. Good question. So yeah, so for all these applications, it is important to understand and be able to predict this kind of energy dissipation through fracture. That's the focus of this project. This is another chart which actually compares composites to some other materials. Now this chart on the x-axis has the strength of the material, and on the y-axis we have the toughness. So it is very important to understand that strength and toughness are actually two different concepts. Strength is just how much maximum load a certain material can withstand before it breaks, whereas toughness relates to how much energy it can absorb and then dissipate upon fracture. So when you say something is strong, that doesn't necessarily mean it is tough. And we want the material to be tough, okay, to dissipate a lot of energy of impact. So some of the materials here which have a high strength, is the cursor visible? Does the mouse work? Actually, at this point. But let's see. The bottom right part of this chart shows materials which have high strength and low toughness. And these include ceramics. These are like very strong but brittle. So they need to apply very high force to break them, but they break easily once that force. Materials which are on the top left part, these are like some kind of polymers. So they break at smaller values of load, but you have to stretch the required weight. So this that. So ideally we want both strength and toughness, and you see that composites are right there on the top, with other materials like steels, and copper alloys. They have both high strength and high toughness. So toughness is the property that we are interested in for energy dissipation. It is directly related to energy dissipation. So I'll introduce a property here which maybe some of you have heard of. It is called fracture energy. Okay. Fracture energy means the energy required to create a new surface of the unit area of the surface. That is basically the energy required to break it open, basically. And that is nothing but it's related to this toughness. So that is the property we will be talking about mostly during this talk.
You talk about toughness. Does it mean when something is fractured, as in a car, when it's bent, or can you repair it? Is that toughness?
Yeah, no, that's not tough. Usually these events of like fracturing, they are like thermodynamically speaking, they're irreversible. You cannot reverse it because energy is dissipated. If energy is not dissipated, of course you can recover. But when energy is dissipated, it means the event is irreversible. Fracture, by definition, is irreversible, and therefore you cannot. I mean, you can repair it by applying some additional material or like patchwork, but like not inherently. Like the material cannot be reversed. Another great question. So here I will be showing a video of test being conducted by NASA of crashworthiness of a fuselage of an airplane.
You want me to take one in your grade?
This is a section of the airplane fuselage.
Thank you, Justin.
And they do this kind of drop test.
6, 5, 4, 3, 2, 1, release.
absorbed by this kind of impact. But it is very expensive to do these tests. And you can only do one test, right? Like once you do the test, the fuselage is broken and you cannot reuse it for another test. So you have to, if you have to do, let's say, 10 tests, you have to make 10 components. And that shows truly the value of being able to build a computer model which can meaningfully, be produced in results and then ready to happen under different places. And this emphasizes again the need to understand and predict dynamic traction of model structures. Of course, I am not going to say that you can replace testing with modeling. I do not believe that you can completely replace. You have to do some testing, but you can do some testing, validate your model, and then use the model for a lot more cases to validate. Okay, so everybody agrees? Great, we can use a model. But there are, of course, a lot of challenges in doing that for composites. And that is what I will talk about next. So this is a plot showing load on the y-axis versus deformation, stretching on the x-axis. So typically what is done is to measure the fracture energy, the energy required to break a material. You do a lab test with a specimen which already has a small crack in it, and then you load it until the crack grows, and then you measure the area required for that crack to grow, and then you divide it by that area of the crack to get this fracture energy. Okay. Typically this is done for many materials, it's a very standard test. There is an ASTM standard and so on. The problem is for composites, because they are so strong and so stiff, as soon as they reach that peak here, like you look at the blue colored plot, typically for materials after reaching the peak, the crack starts to grow, and then the load starts to decrease at increasing elongation, deformation. And this area shown by the blue color, that is the fracture energy. For composites, what happens is actually the equilibrium path has a negative slope. Right? It cannot follow this nice, smooth decrease. It goes in the reverse direction because the energy is so high that it cannot do this kind of softening in a stable fashion. And so what happens is, as soon as the peak is reached, composite will break.
Whoa.
So this is a very unstable test to perform for composites, and this has plagued researchers for decades. How to measure the fracture energy of composites? And if you look for literature, you will find very rarely this value is reported. We don't know what is the fracture energy of composites because of this unstable behavior. Okay. So this is one big challenge. If we don't even know what is the fracture energy, how will we predict how much energy a structure can dissipate upon impact, right? This is one challenge. Okay. Challenge number 2. This is called scaling. Okay. What happens for materials like composites is that the failure behavior scales with size. What does that mean? That means typically as the size of the specimen or the structure becomes larger and larger, it starts becoming more and more brittle. It starts resembling more of a brittle material like a glass. And when you start making the specimen smaller and smaller and smaller, its fracturing becomes more ductile, more like a metal. This may be like if you are engineers, you take some course, this may be a little bit difficult to grasp. But for materials like composites, this does happen. So the failure behavior is size dependent. And there are actually mechanics-based, framework to analyze this, so on. But we need to know this. Why? Because we do tests in the lab on a specimen of size, say 100, but your structure, like an aircraft, which is shown here, is several meters. So how would the failure behavior measured in the lab apply to something that large? So to be able to do that effectively, you have to consider how the scaling of the failure happens. How brittle does the structure get when you go from the lab to the structure? This is the second challenge. Again, something which is not very well known to people, and it is an active area of research as well. that is challenge number 2. Challenge number 3 is that composites, what are composites? They are made up of multiple materials, right? 2 or more. That is basically what is the definition of composite. For example, if you take carbon fiber reinforced composite, it is a polymer and it is reinforced with carbon fibers, which are really strong. These are 2 different materials combined to make one. So inherently it is very, very heterogeneous. Okay? And because of that, this kind of, it undergoes failure by multiple mechanisms. And amazingly, the mechanism by which it breaks depends on the direction of the load. If you pull it versus if you crush it, the mechanism is different. For example, here I show on the left pulling, which is the tension, and that happens, failure in that case happens by individual fibers breaking it. On the other hand, if you compress it, the fibers will buckle locally. They will undergo something called buckling, because these are long and slender structures, so they will kind of buckle. Under shear, it is completely different. Under shearing, the matrix will break, and so on. So basically, depending on the direction of loading, you have many different failure mechanisms possible. And each of these mechanisms dissipates a different amount of energy. So that it presents another challenge for composites. We need to first of all characterize the energy under each of these different modes, which is again different. So yeah, so this is challenge number 3, that the failure behavior is very, very complex. It consists of multiple mechanisms at different scales, and each of these mechanisms dissipates different amount of energy, which you need to effectively predict. And all these challenges are there for a crack which is growing slowly, static, and also for a crack which is growing fast or dynamic. But for dynamic cracks, there is another challenge, which is crack branching. Now, when you load something which has one crack, very, very slowly, the one crack stays one crack and it grows as one crack. But as soon as you start making it faster and faster and faster, crack branches. In fact, for crack branching, you require high-speed loading. When a crack branches, what does that mean? That means one crack becomes 2, 2 becomes 4, 4 becomes 8, and so on. So that means more energy is spent. And why does it branch? Because just because you're loading it so fast, that means it has more energy to dissipate. So one crack is not enough to dissipate all this energy, so it has to branch in multiple. So you have to understand what are the conditions which govern this branching. When does it start to branch? How many branches are formed? And all these things, which are actually very complicated, but these are required to correctly predict energy dissipation. So primarily we will tackle these 4 challenges actually, what I will show. I will not show too many technical details, of course. I will just show you the challenges directly over time and some of our ongoing work. Okay. So to summarize, we have these 4 challenges. 1, that fracture energy measurement is not easy for composites. The tests are highly unstable. 2, the fracturing behavior depends on the size. It becomes more brittle as you increase the size of the structure. 3rd is that fracturing itself is very complex and it consists of multiple mechanisms depending on the direction of the loading. And 4th, when it is dynamic, the cracks can branch, and I will talk about it, but they can also curl, and then all this affects the energy dissipation, which you must be able to predict. Okay. So we will first talk about the first 2 challenges, measurement and the scale. And it turns out that both of these challenges can be kind of tackled together by doing something called size effect analysis. Now conventionally people are used to doing tests with just one sample size. That is no longer applicable or valid for composites. You have to test sizes, samples of multiple sizes. That is what we did here. This is like a slide from actually my PhD work and all that stuff. You can test the same composite but make the specimen of different sizes. And that will actually give you a lot of information about how the failure behavior scales. And without going into too much detail, this plot actually shows the strength versus size. And you can see that as the size increases, the strength decreases, and that also means that it becomes more brittle as size. And using this, you can actually also indirectly calculate the fracture energy, because there is this very well-known law called the size effect law, which you can fit through your data, and then you have these two parameters, like sigma and r, I don't want to go into detail, but these parameters are directly related to the fracture energy. So, like in the past few years, we have started realizing that we can actually, we don't have to measure this whole, like track the crack growth and measure the area under the curve. We can just measure the strength of different sizes, and then use this method to indirectly reduce the fracture energy. So this kind of overcomes the issue with the fracture tests being very unstable, and also it gives a lot of understanding on how the failure behaviors is. For example, when we test something in the lab, for those sizes, we can find out where we are on the spectrum of peptide brittle. And then from that we can tell for a particular structure size how brittle it will be. Okay? So these two challenges actually are kind of overcome by this analysis called size effect. This is very intuitive to something that you may have heard, strength is a material property. That is correct. But the strength of a structure which already has a bracket, that is not a material property. That depends on the size of it. That dictates how brittle or how ductile that structure is. So therefore the size effect analysis is very, very important for composites. And it is actually true for many other materials also. Okay. So this is the analysis this is the approach that we are using. Also we recommend to overcome these two challenges. Solve the stability issue, the test, and also understand the scale. Thirdly, there are these multiple mechanisms of failure. One approach to overcome this is called multiscale modeling. And what this approach involves is you have to explicitly account for the different length scales this material has. So to give an example, basically a composite has a lot of length. This structural level thing is called laminate. Okay? Composite in general has a lot of layers. That is called laminate. Each layer is called a lamina. Then within each layer you have yarns, which themselves consist of individual fibers. Okay? So starting from the matrix and fibers, you make yarns. The yarns form layers, and the individual layers form the lamina. So composite itself, if you think about it, it consists of many lengths. So it's a complicated material. So we have this model called microplane model, which kind of accounts for these different lengths. Individual fiber levels, fiber and matrix, which is the sub-micron level. Then we go to the yard level, which is like a bundle of fibers. Then we go to the layer, individual layers, and then stack of the line. And then depending on which length scale we are, we can formulate the failure mechanism at that length scale. And that becomes very easy. So for example, if we know that tiny cracks are being formed between two fibers, and we formulate that failure at the fiber level. If we know that the failure is occurring between layers, then we formulate that failure at the laminate level. And so this gives a mechanism-based structure to the model, and that helps with not fully, but at least partially overcoming this challenge of multiple failure mechanisms. Okay. And we couple this with this concept called crack band theory, where this is actually a very effective approach to model cracks, especially in large structures. The way this model works is it doesn't explicitly model a crack. What it takes as a crack is material with zero stiffness. So as you start applying the load at given in the model, it will detect where you have highest stress, and then it will start to decrease the stiffness of that point until it slowly reaches zero. That when the stiffness reaches zero, that means that becomes a crack. So it can capture this behavior of crack propagation, interaction of multiple cracks, and also crack branching. But that is still ongoing. Okay. So I will show now some abilities of this modeling approach. For example, this is a measurement of the displacement and strain field from the experiments on the top paper. And the bottom, which shows what the model predicts. You guys don't know, it's pretty good ultimate time. It doesn't look that great, I know, but this is considered pretty good. Mainly this actually. So these are some broken specimens after tension tests of a composite. They are black because it's carbon fiber. And you see how the crack is formed here. On the left, so these are two different types of composites by testing. And the tension, and then on the bottom we show compression. And the model, you see how it predicts a crack in a similar way. So whatever is black, it's like a crack. So it doesn't explicitly model the crack, it just models it like material more stable. And you can see that it is actually fairly effective in predicting this crack here. Mainly it predicts the scale, the size effect that I mentioned. How the material becomes more and more brittle, the model can actually capture that. So you see these circles are test data. So on the y-axis there is strength, and on the x-axis there is the size. The model automatically can capture how the it becomes thicker and thicker as it becomes larger. So what does that mean? That means you can use the model for the structure of any size. Now you don't have to actually physically test it. You have sufficient confidence now that you can capture this failure of multiple sizes, and therefore you can then use it on other structures. So we used it for designing these crush cans. So I will show you some simulations. So this is a simulation that we did on this crush can. So this is simulating the crush.
Just to the slide before, the shape
This?
of the structure in terms of the larger size and the effective size, the shape play a role in that?
That's a very good question. The question was, does the shape play a role? And yes, it does play a role. But what we believe is that, or what can be shown, is that if your model can capture one shape, it can also capture other shapes. What is important is, for the same shape, if you scale it, can it predict that scale? If it can predict it for one shape, it can predict for other shapes. So the model automatically accounts for the effect of the shape. Alright, so this is the cross section of this crush can. They call it the hat section. This was developed by the Ford motor. It's called hat section. I don't know why it has some benefits actually when it crushes. It's not exactly a circular cross section. It's like a plate and then this kind of hat shape section. And we modeled it with the and if you realize, as it crushes, it is a progressive crushing. So it starts at the top. So by the way, this is the crush can be impacted by a plate. Okay. So it starts crushing at the top and it progressively crushes the whole can. This whole event is taking place in less than 1 millisecond. Okay. So it is significantly slowed down for it. But as it basically crushes it, the structure, the crush can resists the crushing through a force. And that force is plotted on the bottom, force versus time. And this is the parameter which these car companies are interested in. They want this force to be one stable, constant value. That means the resistance to crushing is there throughout the crush. And you can see that there are fluctuations, of course, but the model agrees very well with the measurements. And then with this validation of the model, you can then use it to analyze many different cases. So these were some different designs they wanted to test out, and then you can model it. And again, the essential ingredient of this is the fracture energy. If it is based correctly on the correct fracture energy measured through this size method, can match this kind of behavior very well. And then you can use it to design. Right? You know how thick you make it, you know how large to make it, and then how much force or how much energy it will actually contribute. So yeah, so this just shows some sample simulations that we did, And there's a slide showing how important the fracture energy actually is. If you don't have the correct fracture energy in the model, it will predict a force much lower or very different than it actually is. It will directly affect this quantity. And therefore it is again very, very important to characterize it and then use it in very large errors are otherwise possible. Now this was for automotive application. In our project we are trying to apply this to army applications, for example like ballistic impact. So here I show one video of missile impacting a slab. These results are actually different kind of composite. It is concrete. It is also composite, made up of gravel and cement paste. In that case, cement paste is the matrix and the gravel is the beam. But there is also sometimes steel, which is reinforced concrete. But concrete by itself is also composite. So this shows some results of ballistic penetration, missile penetration, and see how we match pretty well the later shapes, but not that well. So this is ongoing. And this is actually different from before because for the crush cans, the impact is like mid velocity, 30 to 35 miles per hour. This is much higher speed, so it is much more dynamic. So we don't know if all these approaches that we have directly works for very, very high speed rates. So yeah, so this is ongoing work that we're doing right now with ballistic impact, and we're also trying to analyze more carefully the branching of cracks. So this is some analysis, recent analysis that we have been doing to predict branching of cracks. You see, as loading rate increases, you see more branches being formed. That is what the model is also trying to show. So that's what I'm doing. On the top right, slightly in a small picture, we show experimental data. So as we are trying, we are seeing that the model also reproduces this. And that is just because there is more energy available when you load it faster. So one crack is not enough to dissipate all that energy. So it must branch. And it seems like it is capturing that. So yeah, so this is where we are. So I'm going to summarize whatever I talked about. First of all, it is important to understand that fiber composites are materials which fail by different failure modes, and we have to understand their failure behavior so that we can safely design structures and also extend lab scale measurements to real world structures. Size effect testing is a very effective way of overcoming the stability issues that I mentioned in measuring the fracture energy, and also understanding how this scales. So you can correctly interpret and correctly extrapolate lab to real world. And then for damage models, you develop models for composites. These concepts must be, like the model must be built on these concepts, and it should also then be ready scaling correctly. So then you can apply it confidently to any structure of any shape and size. And of course, you must capture these different failure modes: tension, compression, shear, and you can use this smear crack band approach, where it doesn't explicitly model the crack, but it kind of models it in a smear fashion where the material is just the stiffness of the material is degraded to zero. For very large structures, that appears to be very effective. So we have this multiscale microplane model which seeks to capture all these different failure modes, and we are now using it to study dynamic fracture, which has important considerations. Branch. Very important to understand that. Right. So yeah, so that's the summary of my talk. I think I finished it early, but I think that's great. So if you have any questions, thank you for listening.
That experiment that you showed with the missile going through the concrete, is that like any type of specific like missile, or is it like just went straight through? Like was it like a high explosive type of thing, or?
No, so this missile, so these tests were actually done by the army. So I don't know that many details about it, but it is basically a projectile. I shouldn't call it a missile. Just a projectile which resembles a missile. They just shot it at a slab of concrete, and then they measured exit velocities in. So you know the inlet velocity, they measured the exit velocity, and then these craters. And this was prediction from the model.
Do they also account for if the projectile starts to tumble when it goes through the material?
Like wind turn?
Yeah.
Yeah, that is a very, very good question. Especially in if you shoot something like in sand, the projectile will turn. So because this was concrete, it did not do that. So yeah, so the answer is actually no. That's a very, very good point. And I don't know how many people can actually predict that. It's very difficult to predict. Alright, so no more questions.